Welcome everyone. And our speaker today is Stepan Kuznetsov from Steklov Mathematical Institute of Russian Academy of Sciences, who will talk on circular and infinitary proofs for complexity analysis of action logic. So Stepan is well known for his work in the area of Lambek calculus and its extensions, including extensions by infinitary and circular rules, and as well as expansion of the language of Lambek calculus, and more generally, all kinds of substructural logics. And welcome, Stepan. So we're glad that you agreed to give this talk, somewhat on short notice, but nevertheless, please begin.
Okay, thank you for the invitation. Are the slides visible?
Yes.
Yes.
Okay, great. This talk has a global. Yep. The global aim to show how infinitary proof mechanisms help proving some algorithmic complexity results for logical systems. Well, of course, these logical systems will be defined in an infinitary fashion, and the complexity results will be very high. It will be not like decidable things, but it will be more than arithmetic usually, or sometimes arithmetical complexity, but yet not enumerable. So the concrete example, the concrete results we're going to present today concern action logic, and it's non-commutative substructural logic, as Lev said, an extension of the Lambek calculus, extended with Kleene star or Kleene iteration, as people call it also. And the basic logic is the multiplicative, additive, associative Lambek calculus, the full Lambek calculus, and we will further extend it with various axiomatizations for Kleene star, yielding infinitary and or circular proof systems. This talk is partially based on joint work with Stanislav Spiransky, who you also see here in the virtual room, and Tikhon Pshenitsyn, my PhD student. Some of the results, the earlier ones, are my own. So before starting the proof theoretic part, which is more relevant to the proof society, I would like to give some algebraic definitions just to give some framework in what we're discussing now. So the classical notion of Kleene algebra, think of regular expressions in computer science. So you have plus, you have multiplication, a union and product of languages, 0, 1, just constant 0 and 1, the neutral for plus and for multiplication, and the Kleene star is the Kleene star. And so formally, what we require from these things that the structure with plus multiplication 0 and 1 is an idempotent semi-ring. Idempotent means a plus a equals a. And a star is the weakest definition we usually use. Well, of course, there could be weaker ones, but out of the two we're going to compare, is the least fixed point of the following operators. And it should be simultaneously least fixed points of both of them. Without divisions, there are some bad examples of left but not right, Kleene algebra, and stuff like that. So it's something which is greater than 1 and survives under multiplication on a. So if you think of languages, then this is really the iteration of language. You can iterate it 0 times, which will give you just the empty word, or you can multiply it by a as many times as you wish, and you will get it. There is natural, as usually in idempotent semi-rings, there is natural partial order, a plus b equals b, which we'll make use of. And an action algebra, or residuated Kleene algebra, is a Kleene algebra with residuals, where you can divide, and division is coordinated with multiplication. So again, on formal languages, you can do this. And this is the root for Lambek calculus. So these traditions were developing separately. So the residuals go back to works from Krul and Watt and Dilworth, and then Lambek introduced them for linguistic purposes. And Kleene algebra goes back to works of Kleene and a good tradition in computer science. Finally, in the beginning of the 90s, von Pratt and a bit later Dexter Cozen mixed it all up and introduced the notion of action algebra. Kleene or action algebra is called star continuous if the following holds. So here, these B and C are actually not needed if you are talking about action algebra. So we can think that they are just units because we can just divide them out. And A star is the supremum of nth powers of an element, beginning from 1, from 0, which is the unit. So the natural examples of action and thus Kleene algebras, they include the algebra of formal languages and also the algebra of binary relations, which motivates the word action here, because the binary relation is like a non-deterministic action on a set of possible states of a subsystem or some worlds, and the natural operations on them. Multiplication is sequential composition, union plus is the union of just a theoretic union, and divisions are conditional actions. So if you first do A, then our action you will get B. This is B divided by A to the left, the same to the right. And Kleene star is very natural, the reflexive transitive closure of an action. And both are star continuous, of course. But examples of non-star continuous Kleene action algebras, they exist, but they are somehow artificial, and nevertheless, this general class is also interesting, this type of class, because they have different algorithmic properties. So if you restrict ourselves to only the star continuous case, it's like the standard model, say in arithmetic, you will get much more complex theories than if you talk about just general, maybe non-star continuous Kleene action algebras, where of course everything is restricted by the class of sigma 0, 1, the recursion enumerable. So here you can see this, that if you consider all Kleene action algebras, then all the theories will be enumerable. And we'll see that very quickly they become undecidable, so sigma 0, 1 complete. But when we go to the star continuous case, then complexity may rise up to pi 1, 1. This is the maximal complexity level we could achieve here. We'll see why, but it's still very high. It's higher than hyperarithmetical, so it's like the first level of second order arithmetic. And we consider fragments of the first order theory. So we have the equational one, where just equations of the form A equals B, and we have the Horn one. So in the Horn one, we have formulae of the following form. It's actually entailing an equation from a finite set of equations. Why we consider such theories? Because already on the level of the Horn theory, we'll get this enormous complexity. We don't have to go higher. So here we will call these hypotheses. For convenience, we'll talk about inequations rather than equations, because we will formalize this as a some sort of substructural logic, and inequation is something like implication. It's easy to axiomatize it. Equations are harder to tackle, but in the presence of disjunction plus, it's the same, as we've seen that inequation is a special kind of equation, and instead of plus we'll write disjunction. I'll also shift to action lattices, so also add the meet operation. For simplicity, I will not discuss like some fragmentary things. Today, what happens if we remove meet? Basically nothing. What happens if we remove both meet and join and consider only the Lambek calculus? Just multiplicative fragment. Something will survive, something will not. I will not talk about this just for the sake of being more straightforward here. So this residuated lattice part. Okay. Yep. The part of all connectives except for the Kleene star, this is governed by the multiplicative additive Lambek calculus, and we'll see the axioms on the next slide. So and it's just a finitary system, just a standard thing. And infinitary or circular inductive mechanisms are used to axiomatize the Kleene star, which is the interesting thing. So namely, in the star continuous case, we'll use either an omega rule, or we can shift also to an equivalent system with non-well-founded proofs. And this is called infinitary action logic, act omega. The calculus with the omega rule is due to Palka and Bushkovsky in the beginning of the zeros. It's like as a sequent calculus, but of course the notion was known to Pratt and Cozen in the beginning of the 90s. And for the general case, we have action logic, which has an inductive axiomatization of Kleene star, and this will be reformulated as circular proofs. So we'll have these two, like arbitrary non-well-founded proofs will stand for, or a mega rule will stand for the infinitary case, and for general case, we'll have circular proofs. Also, sometimes we will shift to the commutative version of act and act omega. So from the point of view of like applications of this, it's like something not so interesting, because as we've seen, our examples of Kleene algebras and action algebras, they are mostly intrinsically non-commutative. So words in a language, they are not commutative. Also, relational composition is not intended to be commutative. But just for, we still can consider these systems, and they are, and we are commutative Kleene lattices, commutative action lattices. And at some technical places, it will be more convenient for us to consider commutative versions, as technically things will become easier. So first, let's start with theoremhood, or derivability from without hypothesis in act and act omega. So and here we get sigma 0, 1 completeness and pi 0, 1 completeness respectively. So they're both undecidable, but they have a disability of a different kind. So for act, we'll get what we're supposed to get, because it's an enumerable set of theorems, and well, there are some exotic counterexamples, but usually if you are enumerable and undecidable, you should be sigma 0 incomplete. For act omega, the situation is in a sense opposite. So it has an omega rule. So it's no way for, and it's actually inevitable as shown by this result. So that doesn't have a finite axiomatization, even without hypothesis. But for on the other side, it has, due to the work of Boškovský and Palk, the finite model property. So its non-theorems are enumerable, and the set of its theorems is co-RE, and it's complete in that class. So when I'm talking about theoremhood, I'm talking about actually the equational theory, because globally we now think about not a Horn formula as just one formula, but we are thinking about entailing equations by equations. And here we entail equations from nothing. So we just think about equations which are generally true, like equalities of in Kleene algebra.
And ACT also has some explicit axiomatization, right? So by
yes, we will see it right now. Yeah. So I don't see where is it. Yep. So MLC will be here. It will follow. Yeah. We will have it. Yeah, for ACT, this is the maximal complexity possible. And we'll see, just because the axioms go by induction, and also circular proofs give recursive enumerable thing. So the same complexity holds for any extension of ACT. You can consider the Horn theory, or even the first order theory of all action lattices. It will still be enumerable, so they all are sigma 0, 1 complete. And for reasoning from hypothesis in act omega, the Horn theory of star continuous action lattices, the complexity escape is much more interesting, and we'll see it. And we'll consider there two cases, the general one and the one where hypotheses are star-free. And in both, there are non-trivial complexity results. More interesting for the second one, actually, but this is the second part of our talk. So just to get started, how we formulate the systems. So we formulate them as intuitionistic-style sequent calculi, as sequence systems. So we will have multiplicative additive Lambek calculus, where we build the formulae from variables and constants 0 and 1 using our set of operations. So we have formulae without the star, and we have the extension of formulae with the star. The star is the only unit operation. All other operations are binary. So meet, join, product, and two residual. A sequence are expressions of this form. On the left, we have an ordered sequence of formulae. This is substructurality. We don't have, so this comma is meant to be a product, and so we don't have any other structural rules. We have weakening, we don't have contraction, and we don't have even exchange. We only have associativity. Because, say, in formal languages, you cannot contract, you are not commutative, and you cannot add anything by making doing it as a weakening. And here's the intended meaning, of course. So the commas get replaced by product, The arrow is the inequation, and if there is nothing on the left, it's possible, then the empty product is 1. And if we consider multi-sets of sequences of formulae, it should be formulae, and here should be sequences. So if we consider multi-sets instead of sequences, then we get the commutative version of MLC and the corresponding commutative versions of action logic. So this is the way not to add officially the rule of permutation, because sometimes it will mess up things. So if on the left we have either in the non-commutative case sequences, or we have multi-sets. And so here we have the full axiomatization for MLC. Well, at any proof theoretic talk, we should have such an intimidating slide with many, many rules, but not so many axioms. So all the axioms are on the first line. The main axiom is A implies A. Also have something for constants. Here we say that comma reflects the product. The rules for divisions, they are standard Gensen style rules for implications, but they are like directed implications. So you either imply from the left or from the right. And it's reflected by these rules. So if P implies A, you have B, then P and A implies B is modus ponens B. And here is the same, but on the other side. And these are like deduction theorems. How can you prove A, like substructurally implies B? You have to derive it from A and everything which was in the constant there. And the order also matters. So here A should be on the left, here should be on the right. So these are the standard lattice theoretic things for meet and join. And also this includes distributivity of them over join over product, which is obvious. And we have cut. The cut rule is a special one. I will talk about a bit about cut elimination, not in detail, but where it holds and where it fails. So the traditional system for infinitary action logic, presented in the work of Eva Palka, uses an omega rule and also an infinite series of rules for introducing it to the right. So on the left, we have the following. If we want to prove that A star belongs to something, so a Kleene star or something is a subset of something, then we have to prove it for any n. So iteration it says that there exists such an n that, and therefore if we're on the left, it will transform into for all. So this should hold for any n starting from 0 up to infinity. So this is the omega rule. It has infinitely many premises. And these are regular rules, but there are infinite series of them. How can you populate Kleene star? You should take a fixed n and populate each a, and then just make the product of them. So in the presence of such rules, you have to be more careful of defining what is a proof, what do you mean by derivable, provable, and there are two approaches which are equivalent. This classical thing going back to early works of many people, like we cite, I think, Peter Axel at this point, but it's like many people knew that, the proof should be, it could be infinite or due to this rule, but it should be well-founded. So it's a tree which is like, it's like actually like a bush. It doesn't grow high, it goes like wide. It cannot have infinite branches, but it can have infinite branching. And the alternative approach is to define the set of derivable sequence as a minimal set, which is closed, includes all the axioms and closed under rules, and this yields to a fixed point definition of that, and we'll see it later. So for action logic act, again we have the following, as Lev asked, the following formalization of induction. So here is like only the left Kleene star, but in the presence of division, they're equivalent. This can be proved. So what does it say here? The left rule, again, is more interesting. If I want to prove that A star belongs to B, we should say that the empty word or the unit belongs to B, is less or equal than B, and also it survives under multiplying by A. So this exactly reflects the fixed point condition which we see here, the left one. The right one is in the presence of division, it follows. So this one, this is the condition. And the right rules are basically the same, and they say that, well, you can use these rules actually, which were with the system in the omega rule, but here they also are formulated in like this induction style, that the unit is less or equal than A star, And if you have A and A star, you can combine them and get a bigger like A star with the same A star. So the cut rule in the latter system with this induction, it's not eliminable. You can see it from the form of these rules. The left, this rule, fixed point rule, obviously it's not in against and style, it doesn't have any context, anything like that. And no cut-free system is known. It's an open question. And in act omega, a cut is eliminable for, of course, if you derive without hypothesis, and this is due to Palka 2007 standard argument. So it's a transfinitization of the standard cut elimination procedure in the Lambek complex. Nothing special happens here, but this is true. So the theoremhood problem for act omega is pi01 complete. But in general, and we shall show how it's proved, in general, such systems with omega rules could reach up to pi11 completeness. So here both the upper and the lower bounds are non-trivial. And they're proved first by Palka and the second by proof. Theoremhood in XCT is sigma01 complete. And the same holds for their commutative versions, and this is what we're going to actually discuss. So recall that here the left-hand sides are multi-sets of formulae, so order doesn't matter, but multiplicity does. The number of formulae matters. So in order to go further, let's reformulate act omega as a calculus with non-well-founded proofs. And the inference rules for the new system will be as follows. So here you see we made them infinitary. So these
may I interrupt you because I had a question for the previous slide. So, so you said that this cut-free system for ACT is an open problem, but you have the result that it is sigma1 complete. So I suppose this means that the cut-free system, hypothetical cut-free system, cannot deliver decision algorithm, right?
It won't. It won't. Nothing can.
So, right. So probably this also means that there is no subformula property for any hypothetical cut-free system.
No. In substructural logic, this is not the case. So consider, for example, propositional linear logic, where instead of Kleene star we have bank. It has the subformula property, but it doesn't have multiplicity matter. So the number of copies of this subformula could be arbitrary.
Right.
And so, yeah. So this is
a similar effect can happen here, indeed.
It could happen here, and one of the good candidates could have been the circular system. But in the circular system, cut is also not eliminable, unfortunately. So say a cut-free circular system will not contradict any of these complexity results. Because if you see the rules, here it's a base subformula property, right? But here it's longer. You add another A, and you can add many copies of that, and you don't know where you
there is no bound on the number of.
There's no bound on the length of the cycle, for example, on the size of the proof. But even that doesn't work, unfortunately. And this is a question. So Peter Gibson tried to solve it, but he failed. One of the examples. Matti Pentos also, he had a preprint on that. But again, it was a candidate, but there were the cut elimination failed.
Okay.
So Peter Gibson actually even implemented it as a semi-prover. So he claimed that many interesting facts are still provable there. And so you can try, but if it doesn't prove, then it doesn't mean that it is not proved. Well, now we know why, because it's undecidable, but that much.
Okay.
So this looks like a very weak set of fixed point rules. However, now we allow infinite paths in derivations, and this makes the system again infinitary. And this is an alternative way of doing this stuff. So there is a validity condition, which is quite a traditional one. So every infinite path should contain a valid thread. So you should have a chain of the same A star, so which is inherited by its individuality upwards the proof, and this A star should undergo this rule infinitely many times. So actually, mostly, almost every cut-free proof is valid. And this makes the system very, very nice and good, because usually checking these correctness condition is like very hard, both if you do it by hand for a concrete proof or try to make an algorithm on that. Here you don't need that. The only problem which could arise is this rule, which can be used with an empty pi just infinitely many times, and it will, if A is derivable from nothing, then you can make a bad like infinite thread, which won't prove anything reasonable. But here you can make pi always non-empty. You can add this restriction, because otherwise this rule is meaningless. It's just the same premise and the same conclusion. And then if your proof is cut free, then it would have to be valid. And this is just due to the fact that all other rules, they make the, say, sequence simpler. So if you try to if you try to make an invalid infinite path, then you will just run out of formula at some point. And therefore, this is a like trivial correctness condition here. And this system, ACT infinity, it enjoys cut elimination and proves the same theorems as act omega. In a full generality, this is due to the work by Anupam, Das, and Damien Bose, and we will not really use these facts in their full generality. So as we'll see further, well, what we really need is something easier. So in particular, we can represent the omega rule in like a vertical form as an infinite branch. This branch will be correct, because this is this very A star which is progressing here. And next, non-well-founded proof is called regular if it has only a finite number of non-isomorphic subtrees. And this means that it's intrinsically finite and it can be represented as circular proof. So proof with backtrack. Once you have a subtree. Inside this subtree, you find an isomorphic copy, and then you just say, okay, I don't need to develop my proof anymore. I just remove all the stuff above and put a backtrack. And this is a classical example. So this formula on the bottom is called pure induction by von Pratt. Or sometimes people call this the second line from the bottom, this pure induction. What it says? It says I have pi, and I have pi implies pi, and I iterate it any number of times, and I will get pi, of course, in the end. So this implication is not like classical implication, because this will be obvious. It's like action implication. So I have done pi. Then I say, if you already did pi and I do the next action, I will get also something of type pi, and so on and so forth. And Pratt said that, well, this is the purest form of induction ever. So it's like simplest representation of inductive reasoning. And here is the circular proof for that. So if you want to prove this, we first say that this could be zero. So this star could say for nothing. Then it's P implies pi is okay. Or we chip off one of these things, and then we just apply one of the rules of multiplicative Lambek calculus, and we get the same formula as here. And we will get a regular infinite proof, non-well-founded, but here we can circle it down, and this will be a finite object which makes this true. Of course, you can also prove it using this least fixed point principle, but here it's much more natural to do it in a circular way. And circular proofs prove exactly the same theorems as in ACT, also proved by Anupam and Damien, but here cut is not eliminable, unfortunately. So in our arguments, we'll need only translations of very simple circular proofs, and actually, this is like a bit of a thing where you become dizzy when you try to really understand these arguments, because if you are talking about arbitrary circular proofs, then they could be somehow complicated. The branches, the cycles could entail somehow, and you should find some non-trivial invariance to code all this stuff. But in our argument, we'll need to translate only very simply structured circular proofs, as we will see in our complex stack. Cut is not eliminable. This is the standard one of the standard examples. It even doesn't use divisions. It's only in the Kleene language of the Kleene star. So here, if you try to prove it, you can decompose something on the left, but at no point you can decompose this disjunction and make the choice, because this star is always on the left, and you don't know whether it's even or odd.
And if you
So
don't have
here we see
disjunction, if you don't have additives in your language, for example, will cut be eliminable?
well, I think no, but I don't have an example at hand.
Mhm.
I don't believe it will be eliminable, unfortunately.
Mhm.
But it's a good question. I think I should make a remark on that, because I don't have it just to show you. So here we don't have divisions, and actually in there, it's beyond this talk, but I will mention that. If you don't have divisions, you can make a cut-free circular proof system, which was developed by also Anupam and Damien, but in another paper. But there, things are more complicated. So in this language, it won't work. And there is another sequent language where on the left, you will have also a meta-connective for the disjunction. So you see what is problematic here, the disjunction. This is actually the characteristic counterexample. You can make it work by saying that on the right, you have not one formula, but like also a meta structure with meta disjunction. And this will give you a cut-free complete proof system, which is circular. And by the way, if you don't have divisions, you will not have addressability here. And these fragments of the star continuous and general cases on the level of Kleene algebras, they just coincide. And they are both the same in non-well-founded and circular, and they are both p-space completed, the same theory. Here, there's a difference. So act amiga is different from act.
So you can call them positive fragments, right? So it's not divisions.
No, well, it's just Kleene algebra. It's the equation of theory of Kleene algebra. Things actually, these results were well known much earlier. It's like something.
And
but from this structural proof theory, you can also get this. By the way.
So what do you mean by in your arguments you use only simple circular proofs?
We will use these circular proofs to establish some complexity, to encode like Minsky machines. And they will be encoded by concrete circular proofs. And working with, we don't need to analyze arbitrary circular proofs. We will need to analyze like just concrete, we'll just construct it, which is much easier. We'll see it now.
Okay.
So we will, more questions?
Not from me.
So we will, for simplicity, as I said, we will prove, at this point, we'll talk about commutative versions. And we encode Minsky machines. So Minsky machine, we have like 3 counters. Well, you can do with 2, but I prefer 3. We can say for religious reasons, that doesn't matter. It should be more than 1. So, and we'll have 3 possible operations. So you can increase 1 counter and change the state. So a machine has a state and 3 counters. You can decrease the counter, but this application is licensed only in the situation where you have it positive, because they are natural numbers, they're not integers. You cannot decrease 0. And also there is this jump on 0. So you just perform a jump, say you change your state, but without doing anything to the counters, but it is licensed by the fact that one of the designated counter C is 0. Sometimes these are made just in one operation. You just if and else here. So here A is, and these are the formula which will encode them. So they're obvious, and we'll see how they will work in the proofs. So having P, give Q and 1 copy of C, which says that this is a counter, the number of letters. So given P and C, return Q. Here take P, return Q, but you also need to license that C is 0, and these are special pseudo states for 0 check. Each configuration is encoded as follows. Counters are encoded just as copies of the same letter. And this is regular expression which encodes any valid configuration. Either you have a normal state and you'll have something in the counters, or you have 0 checks and then you check that it's actually 0. So see here you don't have A, here you don't have B, here you don't have C. And this is the oh no, I think it should be conjunction here, I think, right? Yeah, it should be conjunction, sorry. So all should be, yeah, it's very bad. It should be all conjunction, and here should be division. So Yeah, so this is the source of, maybe I'll even change this because otherwise we'll be fast. Okay. So here we have, so let's just switch. Sorry for that. So here we have all our instructions which came from this. And also we have special dummy instructions for filing. So dummy instructions for Z. These are like pseudo states for checking for 0, and they should. Yep, it's now it should be good. Yep. So this should be. Where is it? Big wedge. Why doesn't it? It should be a big wedge here. So nothing happening. So good. Maybe we'll just reload the slide. Okay, I will do it once more. Okay. And I will share. So share, and we see it here, right? Share. Okay. Okay. I
Right.
it's visible, right? So this is the source of instructions, and now we what are we going to do? We're going to apply them. So the easy so the easy instruction is the increasing, and it works rather straightforwardly. So you have this stuff like that, and you have this P, and you have a copy of A. You add a new copy of A here, and it's here, and then here. So it's one application, and here we use this branching rule, and at each point it actually also checks that this is a correct configuration. This is written here that P A B C is under D. It's okay. So the same for decrement, but for 0 check, we'll need to have a small circular thing here. So here we try to apply this rule with A is actually 0. We apply it, and here we have to open up this disjunction. So you have Q, and there you, so these green parts are like the continuations of the computation. So we came here, and we go farther from here. And here again, the computation comes from green to green, but also this small circular proof validates that the 0 check is okay. And here it checks at any point that this does not include A, because otherwise this will be not provable. So this is how we encode that. So I've shown only the easy part from computation to derivation, but in the infinitary system, it works both ways. So you can also prove that if there exists a normal founded proof, then you can obtain a computation, and it will be an infinite computation, because at each step you are normal founded. At no point you can stop, because you have always an E star here, and E star does not amend it to D. So it means that you have go further and further, and a normal founded proof represents an infinite computation.
And what is D here? I missed this.
D is the regular expression for any valid configuration.
Okay.
D is needed for checking that at any point you didn't do anything wrong. You got, so otherwise you could have just removed this E star, for example. So as I said, the converse also holds. So this system is pi01 hard. It encodes infinite runs of machines. Circular proofs, on the other side, can simulate circular computations. So if you have a circular computation, at some point you have 2 copies of the same configuration and the same sequent, and you can make everything circular. And this proof can be easily translated into a proof using induction also. This is a simple circular proof, and like you can do it just explicitly. But unfortunately, this is insufficient to prove sigma 0, 1 completeness of COM-ACT due to the following problem, that there are some non-circular computations that are also simulated by circular proofs. This is an example. I won't go into detail, but it's like a machine which just increments one counter. Formally, it's non-circular, but it's very regular behavior, and this is a circular proof which simulates it. And so we use, in order to prove undecidability and sigma 0, 1 completeness for COM-ACT, we use the indirect technique of effective inseparability. So here we have this picture. So we have circular running machines, we have halting machines, and we have the derivability of this sequent in our logic, which includes the circular runs. We know that it strictly includes them, but it's doesn't intersect the halting situation, because COM-ACT is weaker than COM-ACT omega, and COM-ACT omega encodes only infinite runs. It cannot encode a halting run. And then we have these two sets with the black ones, and they're inseparable, which means that there is no decidable set which separates them. Therefore, this green set is undecidable. And also, they're effectively inseparable. And therefore, since it's enumerable, then it's sigma 0, 1 completed. Good old basic theory algorithms. So for the non-commutative case, the arguments are like similar but more sophisticated. It's like an indirect encoding. We're writing now a paper with Anupam and Abhishek there, where I tried to isolate this argument and make it more like well understandable. But still, you need something. You cannot just talk about Turing machines. Unfortunately, you have to talk about grammars, which makes things a bit more complicated. So for pi 0, 1 upper bound, I think due to lack of time, I will go quicker here. There are many ways to prove it for ACT omega. So Parker did some like specific proof theoretic techniques there. One of the simplest way of doing it was in Anupam and Damian's paper, where you just say that its validity condition is trivial, so the existence of novel founded proof actually is the same as existence of all its finite fragments. And this is pi 0, 1. And yet another argument which we'll need is based on the notion of closure ordinal. So now we return from the non-well-founded world to the world of well-founded mega rule proofs. And we say that there is an immediate derivability operator, which extends any set of sequence S with set of sequence derivable from S by one step. So it includes all the axioms, everything derivable from one step. So start with an empty set, then you add all the axioms, then you add everything derivable in one step. If the calculus were finite, in omega steps we'll get all the theorems, but with the omega rule is not the case. Obviously, monotone operator, and the set of theorems of our logic is nothing but the least fixed point of this. And there is an ordinal, of course, on which this fixed point is achieved. So the small alpha where this sequence of powers of this stabilizes, and it's called the closure ordinal. And since it's an arithmetical operator, its closure ordinal is bounded by omega 1 Church Kleene, the first non-computable ordinal. For anything, it will be at least omega, not more than omega 1, but here it's effectivized into omega 1 Church Kleene. However, for ACT omega itself, a simple ordinal complexity measure shows that the upper bound is much smaller. It's omega power omega. And this will be a good ordinal for our purposes, the main ordinal we're going to think about. What is good about omega power omega is that below this ordinal, you have a marvelous system of ordinal notation. It's the counter-normal form. So it's just polynomials of omega. You don't need to refer to something more sophisticated like Kleene's O, for example. Here you have just one-to-one notation into natural numbers. Everything is computable, everything is nice. So the measure works naturally. So each time you take any variable as 1, then if you do a binary operation, you just add them component-wise in the counter-normal form. And for a star, you multiply by omega. And also add 1 just for the star itself. Actually, in fact, what's going on here? So each rule strictly increases this measure. You can see, because everything here plus 1, you introduce a new connective and you increase. And when a Kleene star, in the omega rule, you will have a power n, but omega is greater than any n, so you will get a shift. So therefore, at level omega power omega, you will get all the theorems you wish. but if you derive without hypothesis, otherwise everything fails. We'll see it later. So, in fact, for cut-free proofs, Tikhon Pshenitsyn proved that it's the exact boundary closure ordinal. For proofs with cuts, we don't know. Maybe it could get reduced, but it's unknown. Yep. So if a sequence has measure mu and is derivable, it belongs to the muth power of d taken from t. And another crucial property is the locally finite proof search. So for each sequence, there is only a finite set of possible rule applications which could be used to derive immediately, I believe. I mean, so you have to choose one of the connectives and you apply a rule and find the choice of that. And therefore, we have D is a pi01 operator, because the only thing where you need something complex is the omega rule, where you say that the premises should be provable for all n, and this n is unbounded. So the quantifier, as I said, choose the rule is bounded, and the only unbounded quantifier is the for all over the premises of the omega rule. And the proof of pi01 boundedness of the logic can be now finished by like omega power omega iteration of pi01. So this is formalized by effective transfinite recursion. We will identify ordinals with their natural notations encoded as natural numbers, also identify each sequence with its Gödel number. So now we show that the following set is uniformly pi01 definable. So there is a function which, given an ordinal which is less than omega power omega, returns a pi01 formula which defines the corresponding set of a derivable sequence of the corresponding rank. And this is constructed. Yeah, once it is constructed, we will say that just take the pi01 satisfiability, a formula which means basically that this phi of mu of s on s is true. And here we utilize the fact that truth of pi01 formula itself can be, on Gödel numbers, can be expressed as a pi01 formula. So, okay, this is done in the following way of using recursion theory. So we first do this thing. So we say that the following, we take E, and this should code the program which performs the recursive calls for smaller ranks. So we say that there exists a rule introducing, we want to say that S is provable. And we say how to say that it's provable. We say that there is a rule which introduces this. This is a bounded existential quantifier, so that's nothing. So for all S prime, which is the premise of this rule, in the case of omega rule, this is a real universal quantifier. In all other cases, it's just like a small conjunction. And so it says that for all Z, and now something strange starts. It says that if we compute this the recursive function with number E on mu S prime, you will get Z, and this Z should be a formula, which a pi01 formula, which should tell us about the derivability of sequence of rank rank mu of S prime, and here we'll have S prime. So it should say that it's this formula pi01 formula coded by Z should be true on S prime, which means that S prime is derivable. So this is a recursive call, but still E is an arbitrary number. It's not like the real recursive call, and we'll use the magical recursion theorem to fill it in with the correct thing.
And what is mu here once again? So
mu is the measure. It's the ordinal which measures the complexity of a sequence.
Okay.
And so we identify it with a natural number because it's an ordinal less than omega power. And we actually do induction on that, transfinite induction. And here is presented in the form of recursion theorem. So this is itself a pi01 formula because the first quantifier is bounded. So now we consider the following function f, which says that mu of s is alpha and psi e of s. where S is, so it's a Gödel number, and S is just a free variable in that formula. And now we take the H with a total computable function, which returns the code of this lambda alpha f of E alpha. So E as a parameter and alpha is the argument. And now we, by Kleene's recursion theorem, find a fixed point, which says that E should be the same as H of E, which basically says that this should substitute a recursive call. So I don't have time to go for more details. In the slides, this formula are given, and now we say that this does the job. So actually, it's a very general argument that you can do if you have ordinals up to like omega power omega, for example. You can do computable transfinite induction or computable transfinite recursion here, and obtain. So what we really have, we want to define by transfinite recursion a function which yields the Gödel number of a pi01 formula using the values of the previous ordinal. And we claim that this can be done, and this can be done in a pi01 way. So this is what is going on here, basically. So now what we get the pi01 upper bound on the actual logic. So one can say, why is this? This is maybe one of the most complicated proofs of this upper bound, but it's more robust than anything else because we need only the omega rule style formulation of the logic, and also we'll have some good extensions of that. Both, before going further, both the local finiteness and the bound on the closure ordinal are important, and there is an open problem here. If we add distributivity law, then there is a cut-free system, actually an extension of a system by Kozak. And well, here on the left-hand side, we'll have two metaconnectives. We'll have a new metaconnective for additive conjunction. And for the latter, all the structural rules are allowed. And while we can still make it locally finite, we can somehow harness contractions. We yet don't have a computable bound on the closure ordinal. And it could be omega 1 Church Kleene, and then the whole system is pi11 complete. So this is an open question. And now I have a little bit of time left. The newest part, and maybe the most interesting here. So an interesting generalization is proving from star-free hypothesis. So for Kleene algebras, a star-free hypothesis on the star continuous case, they get pi02. It's resolved by Dexter-Cozen, not so high. So pi02, okay. Now let us consider durability in act omega from finite sets of sequences, hypotheses, and they do not include the Kleene star-free hypothesis. So we may assume that all the sequences are of the following form, or otherwise we just divide everything to the right. And there is cut normalization, that all the cuts can be normalized like this. And for convenience, we make our system dyadic. We add just our hypotheses, which are formulae, into the left-hand side. And this is just a set, finite set, and this is the rule. Cut rule becomes this rule, which we call absorption. And next, we replace all the rules except star L omega, the omega rule, with a one rule fin. So it has a finite, so it's any combination of finitary rules. It has an arbitrary finite number of premises, and we say that we can derive the conclusion from these premises using any of the finitary rules except the omega rule. So we just have a system with two rules, fin and the omega rule. And the new ordinal measure, which ignores anything without the Kleene star. In particular, it includes it doesn't take care of the hypothesis. It says that if you have a Kleene star, multiply by omega, add 2, and everything else just passes through. And in the end, you just add the 1 for technical reasons. And this is needed to avoid the problem with this absorption rule, because the absorption rule, usually this, by the way, yields undecidability in substructural logic, because you can add many copies of A. But they are all star-free, so their measure will be 0. And we don't take care of them. So, but here's +2 to use subfin. So this D underline is the immediate derivability operator. Okay, again, if it has measure mu and is derivable, then S belongs to this mu iteration. And it is thanks to a +2 in mu of A star. So when we apply the omega rule, we absorb all the things above it. So we say that I have derived something. When I apply the omega rule, then my mu got less by at least by 1. And then also above this, I have a fin rule, and this I spend one more element for this. So it's therefore the same happens. This mu ignores the fin, but it takes care of the omega rule. And the fin can be made big, so you never have fin above fin. This is meaningless because they can be shrinked into one fin. And the lowermost fin is taken care of by the +1 in the middle. So the closure ordinal should be again at most omega power omega. We know that it is omega power omega, at least in the cut-free case, because it's an extension of the system. However, the proof search is no longer locally finite. And the operator itself is not sigma pi 0, 1, it's sigma 0, 2. Because fin, you have a non-trivial existential quantifier there. And indeed, derivability from hypothesis is undecidable, so it's not bounded, essentially. And now we have alternating quantifiers, and we iterate them over omega power omega, and we get a hyperarithmetical upper bound. And here we have all this machinery going on further and further, so we have to define the hyperarithmetical hierarchy. We do it in the simplest way by iterating the Turing jump. At the limit case, we take the disjoint sums of the elements below. So this is going to be our echelon pi sigma 0 alpha complete set. And on limit levels, we have sigma and pi being the same. And this is not absolutely standard terminology because usually people add one extra j here, but we need exactly this. We exactly need the limit. And now we have some notations. We have the sigma 0 n formula, which defines the graph of functions on sets. So it's x, big X is the second order variable. And what we are going to show that if we iterate this alpha times, then it's reducible to the alpha plus something level of the hyperarithmetical hierarchy. And this something is you need to add these n's which come from here. So this phi adds some arithmetical complexity. So on the non-limit steps of the hyperarithmetical hierarchy, we'll need to add something, while on the limit steps, we will get the same. And now again, we do the recursive, the computable transfinite recursion. We start with the fact that if you add this extra like operator, which is arithmetical, say sigma 0, 2, then it will add n times Turing jump. And now we'll construct a function which reduces the alpha's iteration of this is our D, to this thing, which is J lift n alpha. And again, we proceed by transfinite induction. On limit steps, we exactly add this n. So this is why the lift here comes. At each limit step, we have to add n, the kn there. And not limit, on the successor steps. And on the limit step, we'll just, we have already constructed everything for lesser ordinals. And we use that for constructing on the limit level. Again, by this psi e alpha, whatever it means, where e is our like recursive call. So again, notations here are absolutely unreasonable for people, but if you try to understand it on a bird's eye view, it says that you have to say that at a limit level, there should exist some smaller beta for which we make a recursive call and answer whether it is true. And finally, we take all the cases together and apply the recursion theorem and get the job. So at limit cases, we use this H, which comes from here, and G. So now on the omega power omega level, we'll get it's a disjoint sum. And if alpha is less than omega power omega, then its lift is also less than omega power omega. So we get a reduction of d omega power omega to h of omega power omega, which gives us the sigma 0 omega power omega boundedness. For act omega, also for commutative version is absolutely the same. It doesn't change anything. So, and in fact, what is the interesting thing about it is this complexity bound is exact. So we also have a lower bound, which I don't have. It's beyond this talk, unfortunately, because this is the job by Tikhon Pshenitsyn, by the way. So when I'm talking about literature, I will say necessary credits. There is a way of encoding infinitary propositional sentences of rank bounded by omega power omega, and even reasoning from monadal inequations is going to be sigma 0 omega power omega complete. So also it gives a robust lower bound on the closure ordinal, which does not depend on the concrete way. And for reasoning from arbitrary hypotheses, we have pi1 completeness, which goes back to Cozen for arbitrary Kleene algebras without divisions, are continuous ones. And as a corollary, we prove that there is a closure ordinal is exactly omega 1 Church-Kleene. So otherwise, we iterate the immediate derivative operator over a computable ordinal, which gives a hyperarithmetical upper bound, which is not the case there, because pi1 is not hyperarithmetical. Okay, so this is the end of the talk. Thank you for your patience. Just some references that these are the papers all this started with. So on the first slide of these two, I've put the papers on Kleene algebras. You will see Pratt, Cozen, Bushkovsky, Palika, Kozak for distributive system with that open problem, and Danupam and Damian for non-well-founded proof theory. Here we have just some selection of classical, mostly classical things on recursive theory or recursion theory, which were used for these hyperarithmetical things. Ash Knight, Moskovakis, Rogers, and this unfortunately unpublished yet book by Montalban, from which Tikhon took these things about the infinitary propositional formulae. So, and these are the papers on which this particular talk is based. The second part, which is about this sigma 0 omega power omega and this pi1 and stuff like that, based on these two papers, this recently accepted and published in Journal of Symbolic Logic. So here are three authors. The lower bound, the sigma 0 omega power omega lower bound, is due to Tikhon. And this transfinite recursion, which will give the upper bound, is due to Stanislav. So here we had the joint paper also with Stanislav on infinitary logical exponentiation. This features the alternative proof pi0 upper bound and the pi1 stuff and omega 1 Church-Kleene. And the first part of the talk was given in these two papers, action logic and decisive commutative action logic, and also something was taken from Boshkovsky and Palika's papers. Okay, so thank you for listening.